Okay, let's go ahead and get started here. Today we're going to do a couple finishing lectures. Well, we're going to start the first of a few finishing lectures today, and this is probably the last one we're going to do anything with C language directly. And then the final week of classes, I'm going to talk a little bit about C++, so you're a little bit ahead of the game when you get to your class next semester. We've focused on C language so far. We're going to do a little bit with C++ to at least give you an introduction to that. Now, but before we switch to that, I want to talk a little bit about dynamic arrays and linked lists. And what those are both ways of using dynamic memory allocation to make something match the size of what you're trying to store in memory. And I want to give you exposure to both of those today with programs that do kind of the same thing, but in a slightly different way. So let's get started. So first off, quick review with dynamic memory allocation. That basically it's allocating the memory, the exact amount of memory we need for whatever it is that we're storing. So if we need more memory, we increase the size. We need less, we decrease the size, and so forth. And we looked at these various functions that actually were part of the standard library. So malloc allocates a block of bytes, returns a pointer to that block. Calloc does the same thing, but initializes it to 0. Realloc takes a block that's already been allocated and then changes the size, makes it bigger, makes it smaller, but preserves the contents that are in there. And then we have this free, which releases a block that's been allocated. And to quickly review how malloc works, malloc, you basically pass in the number of bytes that you want, and it returns to us this pointer. It's a void pointer, meaning it has no type associated with it. It's just an address. So it's up to us to cast it if we want to. And really, we don't necessarily have to cast it because a void pointer, it's okay to assign that to something else. But some compilers will give a warning if you do that. But the idea here is take the amount of bytes we want, pass it to it, it allocates that block, return it to it. If it fails, it'll return a null pointer, 0. Calloc does the same thing, except the way we pass it in is a number of items and the size of each. It does the calculation for us, and it returns a pointer to that block of memory. Realloc, we pass in a previously allocated pointer, the amount of bytes we want it to be, the new size that we want it to be, and it returns that pointer to the new one, or null on failure. All right, now, dynamic arrays. The idea here is we're going to use malloc and realloc to allocate a block of bytes. And since in C, an array, even if we statically allocate it, the name of that array by itself just fires as the address of that block of bytes in memory. So we're going to do the same thing, except we're going to allocate the block rather than statically, as we have done in other programs. We're going to allocate it using malloc to give us that block of bytes. And there's really no difference with how we use those after we allocate it. The only advantage of doing it with malloc instead of statically allocating it is they can then use realloc later to make it a bigger size, or realloc later to make it a smaller size, or when we're done with it, we can free it up and not have it consuming memory for our application when we don't need it to. Okay, so we're going to have to keep track of how many items are in the block. We're going to use a variable for that called num items. And we're also going to have to keep track of that address, that the pointer to that block, the address of it. And we're going to use that. We're going to use a variable to store that. It's going to have to be a pointer variable to store that address. We're going to call it dynamic _ array. And since those things are linked, the number of items are determining how big the space is for this dynamic array pointer, the block that points to. They're kind of linked in their functionality. We're going to store them together in a structure. All right, so here's what my structure is going to look like down here. And this is just example code. You could do this differently, but I'm making a structure called dynamic array struct. Inside of that, I'm storing the number of items and the pointer to the block of data. So now this block of data is going to be the right size for that number of items of this type, this struct value struct. Now notice that I did this with a structure rather than just an integer We could have made an int pointer and just stored integers in there. But I did it this way to show that if you want to store something other than just simple integer values, you could just increase the structure. So for example, you want to store bullets. You could have this be struct bullet struct and have a x, a float x, a float y, a heading, a speed, an owner, a lifetime, whatever you wanted to store in here. And then down here, this code would pretty much say the same. It would be a struct bullet struct pointer to that. In the code down here, the number of items is just how many there are. So this gives us the ability now to keep track of a block of memory and how many items it's representing. Now, what we're going to then do is we're going to make some functions that we pass the pointer to that structure to it. So in other words, we're going to pass a structure instance, a pointer to that, the address of that to it, and it's going to perform operations on that dynamic array. So in other words, it's going to say if we want to add something to the array, it's going to make the number of items one bigger, and then change the allocation to have one bigger, and then stick the value in there that we want. If we want to make it smaller and remove something from the array, we're going to look at how to do that. If we want to get rid of the whole thing, we're going to look at do that. And then I also have this function that's just going to print it out to just show it on the display. So let's just focus on a couple of these functions quickly. Let's start off with the add to array function. Now, if you remember, I'm passing in this structure that's of that type I made earlier. So in other words, inside of this dynamic array struct, we had the number of items, and we had the dynamic array pointer itself. Back up just a second, look at that. Num items, dynamic array, which is a struct, a value struct pointer. Now, essentially to add an item to that array, we increment the number of items. So let's say it was 10. We want to add one to it, so we go to 11. And then what I'm going to do here is I'm going to say, hey, if the number of items is 1 after we incremented it, then that means this is the first item, so we're going to use malloc to allocate that. So in other words, if it's the first one, it went from 0, nothing allocated, to 1 being allocated, we use malloc. But if it wasn't the first one, then it's already been allocated, so we're going to use realloc to allocate it. And then notice what we're doing in each of these, whether we're using malloc here or realloc down here, we're just saying it's the number of items times the size of each of those items. And then whatever that returns, whether it's malloc or realloc, we're going to store that back into that dynamic array pointer. And notice this stupid word processor, or the presentation software here, replaces those arrows with an actual arrow. So I'm going to fix that real quick. Okay, so this is what your code will look like. If it's the first item, use malloc. If it's any of the later items, use realloc. And then once we've allocated that new space, it's now at the end of the array, the last spot in the array, which is the number of items minus 1, because the indexing starts with 0. Then go to that and set the value of it to whatever number was passed in. So this is just storing integers. So let's say we pass in the integer 100. We say make this array, dynamic array, 1 space bigger, which is what we're doing here. Add 1 item, allocate the memory to hold that, 1 extra item, and then set the value of that new item, the new extra item, to whatever number we passed in. Add that onto the end of the array. So notice we're always adding things to the end of that array. We make it bigger. There's 1 new cell on the end. Change the value of that, which is what we're doing there. So pretty simple. Now let's also look at the implementation for how to delete an item out of the array. So this is remove from array by index. In other words, we want to say we want to remove an item, and we want to say exactly where the item is we want to remove. Now this gets a little complicated with a dynamic array because it's all contiguous. We can't just take something out of the middle. So the way this is going to work is we're going to take the one that we want to remove that's going to be in the middle of some list. Like let's say it's this one. We want that one to go away. Well, we have to ripple all of the other ones over into that position and then reallocate this to be one smaller to get rid of the extra space on the end. So essentially what we're doing here is we just make a for loop. We say start at the index number we want to remove, and then go while this is less than the number of items minus 1. So go through all the way through the end of the array, except 1 less. And then what we're going to do is we're going to copy the one that we're on. And notice this is less than, not less than or equal to. So we're going to go 1 less than the one at the end of the array. And we're going to copy over the one that we're getting rid of the next one. So the next one goes over that one, the one after that goes after that. So this is us rippling all of the ones after the one we want to remove down one slot. And then after that, we decrease the number of items. And then after that, we reallocate to be one smaller. The num items is now reduced by one. So it's now one smaller. And let me fix this. Okay, so it's kind of the opposite of what we did to add one, except we had to ripple all of them down over that slot that was that's being removed. So this will get rid of an item. So that's the idea for what we're doing. So let's take a look at the full implementation. So I'm going to switch over here, and we're going to look at that. Let me switch over so you can see what I'm doing here. Okay, so here's the code. Let me make this a little bit bigger if I can. And then we're going to take a look at this. So this is my dynamic array example. So here's that value struct that I created. Right now it just has a single integer, but remember you could add other things into there. Float x, float y, float speed, float heading, int lifetime, int owner ID, whatever you want to add to it, size, color, whatever you want, you could add to this structure here. And then here's the actual thing that's keeping track of the dynamic array. And this is where we just tied together the number of items and then the block of data that's been allocated. Those could be stored just in globals that aren't in this array. But by putting them in the array, it simplifies us just passing both of those things together to these functions. Here are my function prototypes for add to array, print array, destroy array, remove from array by index, remove from array by value. Now, let's look at what the main program does here. Essentially, I just made an array of 20 different integers. I go through, and here is my dynamic array variable. That's an instance of this structure up here. So that is where it has the number of items, and it's got the dynamic array inside of that. And I initialize that to say it's got 0 items right now, and the pointer value for the dynamic array is null at the start. So that's us starting out with a dynamic array that's doesn't have anything in it. It's empty. Now, the first thing I do is I'm going to go through and repeat 20 times calling add to array, passing the address of that dynamic array, because that's what these are expecting. These are expecting a pointer. And so this is just adding all 20 of these numbers to that dynamic array. And then I call print array. And then I remove an array by value. I remove the number 21 from that, which is one of the ones that was in there. So that number 21 will disappear from that. We're removing by value. A lot like Python's, you have some list.remove. And then, and this add up here, add to array, is kind of like the dot append on a list. And then we print it again after we did the remove of the 21. And then I do a remove by index, and I'm removing index 1, which would be 0, 1 is this 20 up here. So we're removing that one. And then I'm printing it again, and then I'm destroying the whole thing. And let's go down, scroll down, and take a quick look at the implementation. So remove by value, what that does is it goes through until the array one at a time, starting at 0, goes through all the indexes. It says, hey, if I find something at one of the indexes, or an index that the value matches the number we're trying to remove, then I'm just going to say I'm at the index of the one to remove, just call the remove from array by index function. We could have copied all this logic up into here, but we already have a function that does it, so we'll just call that and do that. Now the remove from array by index, we already looked at that. Basically, we go through from the one that we want to remove, rippling all the next ones down one slot all the way up to the end, and then we reduce the number of items, and then we call realloc to resize it to be one smaller. Add to array we already looked at, basically adds one to it. If it's the first item, we use malloc. If it's any of the other ones after the first one, we use realloc. And then we add the value of that new item in, and it's always going to be the last thing, so num items minus 1. Print array just goes through all of them, and what it does, it just prints out the decimal integer that's the value. And I added this logic here to say, hey, if it's not the last one, print a comma. And then when I'm done with all those, I print out the new line. And then destroy array, notice how easy that is. We basically just say set the number of items to 0, and then free the entire block. We don't have to go through each one to free them. We can basically just say, release the entire block. Now, let's go ahead and run this and look at what it does when we actually run it. Oops, I've got to fix something here. This needs to be num items. And there it is, and you'll notice that, here, let me move this so you can see it a little better. Make it a little bigger. So notice that we add all 20, it says done. Here's what the list looks like after we added all 20 of them. And then we say remove the value 21. So that one's gonna go away. So where it was 40, 21, 34, now it's just 40, 34. And then we remove that index item 1, which is this 30. Or which is that 20, and so now we have 10, instead of 10, 20, 30, we have 10, 30, and you'll notice this list getting shorter each time. And then we destroy the whole thing, the whole list is gone. So pretty straightforward example here, and the reason is because I wanted to show you how easy it was now if we wanted to add other things into this, instead of just a value, you wanted to add, I don't know, like a player list instead of this, you could have a first name and a last name, or a screen name, IP addresses, whatever you want. You can put any kinds of things you want in this structure now and make a dynamic array of those things. So if you want to keep track of a ball bouncing in your game, or particles in your particle effect, or bullets that are flying around on the screen, or enemies, you could put all of the other information you wanted inside of here. And notice that if I added something else like float x, float y, and I were to recompile this and run it, it's not going to change how it behaves. It works the same way as it did before. We just now have extra places to store stuff if we needed to. Okay, so that's dynamic arrays. So let's switch back to the presentation here briefly. All right, so we looked at the full implementation of that. And now let's move on to the second topic today. And that's linked lists. And they're closely related. They kind of do the same thing, but linked lists, instead of allocating things as a giant block, it's going to allocate things as individually allocated nodes. And the node is just big enough to store one number. And there are a number of advantages to that, but there are also some disadvantages, and we'll talk about that in a second. But each node contains not just the data, but it also contains a pointer that holds the address of the next one in the list. And that's why it's called a linked list. We have this node that's holding a piece of data in it, but it's also holding a pointer to the next thing in the list. And then that node has a place for data, and then a place for the next node in the list. And that's going to continue data, next, data, next, data, next. So the last node in the list, how do we know when we're at the end? Well, the pointer value will contain a null pointer, a pointer value of 0. And then the nodes themselves are basically usually kept track of or allocated using a structure. And so the structure would look something like this. The data that we want to store, and then a pointer, a struct list node pointer. Notice this is a struct list node itself. So we're saying this node has a value, but it also has a pointer to another thing that's the same type as it, that will then have its own value and its own pointer, which will have a pointer to the next one, and so forth. So each node has elements for storing data. And again, this could be extended. It doesn't have to just be the value. You could have X, you could have Y, you could have Z, you could have, if it was 3D, you could have all kinds of data that we add to this struct list node pointer. But it also, to be a linked list, it does have to have a pointer to the next one in the list. Okay, so what we're going to do is we're going to allocate a variable to keep track of that list. And this is going to be probably in our main or wherever we're allocating the variable for that. And we're going to start it off as null. In other words, there's nothing in my list when I start out. So we're going to start out with an empty list. And we represent that empty list by having it be a null pointer. We haven't allocated anything yet. There's nothing in there. And notice in linked lists, we don't have to have a special variable to keep track of how many there are. And the reason for that is one is going to point at the next one, is point at the next one. So we can tell when we're at the end of the list when we hit that null at the end. So when I create this, the end is immediate. There's nothing in it. It's empty. And we're going to make functions that interact with that. And those functions are going to be analogous to the ones we made before. We'll look at that in a second. But here's an example of a picture of what a linked list might look like in memory. So here's that main list pointer we created. It starts out with null, but then when I add a node to the list, it's going to allocate a new block of memory, and it's going to point this pointer at that new block of memory. It's going to put a 10, and then that would be null. And when we make another one, it's going to go to the end of this list, allocate a new block of memory, point this pointer at that new block of memory, make this one null, and so forth. So every time we add a node, we need to go to the end of the list, allocate a new block, point the pointer that was null at the new block, make sure that new block has its next pointer set to null, and then put the data into that newly created thing. So this dividing line I have over here, this is kind of the things that are allocated in the main program, just this pointer variable main list. Everything else is done dynamically with malloc. And notice that these nodes aren't contiguous in memory. They're not like an array. They could be in different places, which is going to have some benefits for us later on. All right, so the functions to interact with that linked list, I made them match the ones we had in that other example with dynamic arrays. So here, add to list, print list, destroy list, remove from list by index, remove from list by value. There is one key difference here that you'll see, and that's that some of these have this double pointer, a list node pointer, and we'll talk about that here in just a second. All right, so let's look at that implementation of add to list, just like we did with add to array. We're passing in a pointer to the list node pointer. We're passing in the address of, in other words, we're going to pass in the address of this main list variable. We're saying, hey, this main list variable that's holding null initially lives in memory at this address. And we'll talk about why that is here in just a second. Now, the idea here is what we're going to do inside the code is we're going to say while the thing pointed to by that list node pointer is something other than null, that means we're not at the end. So the only way we're going to get out of this while loop is if the thing pointed to by that list pointer is equal to null, which means the end of the list. So once we get to the end of the list, we allocate a new block of memory for a new list node. We point the pointer at that, and then we set the value of it to the number that we were passing in, and then we set its next to null. So this is what we talked about earlier. We run through the linked list till we get to the end. Once we're at the end, we allocate space for the new node. We set the value of it, and then we set its next to be null to say it's now the end. Now, why is that double pointer used? The reason that double pointer is used is because we need that list pointer, what the value it's holding, because remember it's holding null, so we can't pass by value. We can't just pass a null into this because changing that null will not show up in the original variable back here. We need this to be changed by the function. So we need to pass the address of the pointer so that the function add to list, if this is the first one, can actually change that from null to the value of this. And the only way we can do that is by passing by reference. So we're passing by reference the address of the pointer that we want it to change. And here it is changing it right there. We're saying when we get to the one that has the null in it, go to that address in memory and change it to whatever address malloc returned. Okay, here's the remove from list by index. Same kind of thing here is happening. Basically, we're saying to remove one of these by index, we basically go to the, this works a little bit differently. We're saying essentially go while it's not equal to null. In other words, go and try to find the end of the list. And if I find the index that I'm looking for, getting rid of along the way, then what I do is I take this temp pointer, which was the previous node, or I set the temp pointer. I then set the one that I'm on to be the next. I free the temp one that I had pointed to originally, and then I return. So in other words, if I go back to this drawing here, we're doing this thing. Let's say we want to get rid of this one. To get rid of that one, we're going to save that off. We're going to take this pointer, point it to that address of the next one, and then we're going to free this. So in other words, we're going to temporarily save this off, replace this with that address of that, and then free that. So in other words, we've clipped this one out of the list and pointed this pointer around it. And that's what we're doing with this code right here. And then I return, because once I've Once I've found the one I want to get rid of, it's done. I got rid of it. So once I've removed the one at that index, I exit the function. Now, it's possible that we could go through all of them and never find the index. That's okay in this example, because when I do get to that one where it's, if I didn't find the index, this function will just return and leave the list alone. It won't do anything to it. And what this code after this is how we go to the next one in the series. So in other words, it's not on the one I'm on, go to the next one. And if it's not on that one, go to the next one. If it's not on that one, go to that one. Oh, I found it. Point the pointer around it, free that node, and then return. All right, let's look at the full implementation of that one. So let me switch over to that real quick. And let me make it so you can see what I'm doing here. And let me increase the font size on this too. Okay, so notice I structured these two pieces of code to be very similar to each other, doing the same kind of thing, just in a slightly different way. So notice here's my list node. Here's my function prototypes. This code all does the same thing. It's just add to list instead of add to array and so forth. So this is doing the same thing. It even has the same values. But notice here is where I'm making the struct list node pointer, and I'm setting null in it to indicate an empty list when this thing starts. And then here's the code. There's remove from list by value, remove from list by index, add to list, print list, destroy list. Now destroy, notice, is a little more complicated this time than it was for the dynamic array, that we can't just free the whole thing because it's all spread out in those different nodes. We have multiple mallocs in different places. So what I have to do here is I have to go through each one of the nodes one at a time until I get to the null at the end. And if I find, or as I go through them, I'm saving off that address, freeing the one that is on where I am, and then I'm using that kind of temp to go to the next one. And so I'm basically running through the list one at a time, freeing each one as I go until I get all the way to the end. And that's it for that code. So let's take a quick look at that in action. Actually, let me just compile it and run it here. And there it is. Notice it does the same thing that the other one did, but this is using a linked list instead of using a dynamic array. Now, they both did the same thing, so why use one over another? Let's go back to the presentation for just a second here. All right, so to summarize why we would use one and not the other, dynamic arrays are always a contiguous block of data in memory. They're indexed using that square bracket operator, just like an array is. So that, in other words, they work just like a static array. It's just we have this ability to add items and remove items and change the size of it. Now, removing items can be expensive, mainly because when we go to remove an item from a dynamic array, everything has to ripple down in place of that. So in other words, if I have an array of 1,000,000 things and I want to get rid of the one at index 1, I've got to ripple all the ones from 2 through 1,000,000 down one spot. That can be expensive. Adding items can also be expensive, especially if we're adding to the end of that dynamic array. And the reason for that is reducing the size, usually not very expensive, but adding items can be expensive. And the reason is that if the block of memory it allocated for us has stuff butted against it that's also been allocated, then to move that, or to allocate that and increase the size, it's got to allocate another whole block somewhere else in memory that's bigger. And then it has to copy all of the data out of this one into that one, then it has to free it. So sometimes it'll be really fast if it can just increase it in place. But if it ever has to move that block, it can be very expensive. But with items that are in that dynamic array, indexing them can be really super fast. And the reason is because you index them with the square bracket operator. It just does pointer arithmetic and takes you right to the item that you're trying to index. Now, to contrast with that, linked lists allocating individual nodes in memory with a malloc for each one, those cannot be indexed using the square bracket operator because they're all over the place in memory. They're not guaranteed to be one after the other. The other part about that is that removing items can be very fast because we don't have to ripple anything around in memory. If you remember looking at that code, what it did, it said take the node we want to get rid of, point the pointer from the previous one to the one that was pointing at, and then just free it. So very fast. Don't have to move things around in memory. Also, adding items can be very fast because never do we ever have to copy all of the things in memory to some other place. But indexing items can be very slow because the only way to get to a certain item in the list is to start at the beginning and run through the whole list until you get to the one you're looking for, the index that you're looking for. So in other words, it's kind of a opposite of the way dynamic arrays. Dynamic arrays, removing items expensive. Linked lists, removing items fast. Linked lists, adding items very fast. Dynamic arrays, adding items can be expensive sometimes. Indexing items in dynamic arrays really fast. Indexing items in linked lists can be very slow. So they're kind of opposites of each other. Dynamic arrays, you can use that square bracket operator to do pointer arithmetic. In a linked list, you can't because we don't know where all those things are in memory. They could be anywhere in memory. All right, a couple related data structures that are related to linked lists. There's what's called a doubly linked list, which rather than just a next pointer, it actually has a next pointer and a previous pointer. You can kind of see that here. So from this one that's holding this 2, we can follow the next pointer to get to the 45. And then we can follow the next pointer to get to the 3. But if I want to go back the other way, I could follow the previous pointers to go to the previous ones. And it still ends with a null at the end. And this first one also usually ends with a null in it to say that's the beginning. So it's kind of, you can see either end of that. So that allows us the ability to go not just forward, but also forward and backward through a particular list, which can sometimes be really useful. But it also takes a little more memory because we have to have another pointer stored in here. Another one that's related that's really useful is what's called a binary tree. And it has 2 pointers, kind of like the doubly linked list is, but rather than pointing them at linking them together in a chain, they're linked together in this kind of branching structure called a binary tree. And notice that we still have the main thing over here out in our main program, the main pointer, but it points at a node that has a value and then it has a left and right pointer. And those left and right pointers point at another node, nodes that are allocated with malloc, and that one has a value and a left and right pointer. And now how do we say when we get to the end of the road? Well, we just end up with putting nulls in the pointer value. But you'll notice that one of the nice things about binary trees, or one of the really cool things about that, is that the worst case we would have, if let's say we have a tree with 1 million items in it, how many comparisons would it take us to get to that thing in the tree, to get to that item in the tree? And in this case, it's only 20, because 2 to the 20th is over 1 million. So with 20 comparisons, we can search through 1 million items and get there with just 20 comparisons. And if you think of how fast something like an if statement happens in C, that's almost instantaneous to get an answer out of 1 million things out of that binary tree structure. Now think about what if you had 1 million items, what would be the worst case for a linked list with 1 million items? Well, the worst case would be it would be all the way at the end of the list. It would take 1 million times. And the average case would be 500,000 times. So using a binary tree, we can get to any node in that whole list with 20 traversals rather than 1 million that we would have with, or 500,000 that we would have with using linked lists. So binary trees, super powerful, used for a lot of different stuff. They also can encode hierarchies and things like that. Now, a couple other related things. Heaps, it's kind of a special form of binary tree. Quad trees are kind of like instead of branching 2 ways, they branch 4 ways. There's an occ tree that branches 8 ways. And those are used for kind of both 2D and 3D voxel-based systems, respectively. And then the red-black trees are used for AI and decision-making. Basically, you assign alternating signs to the different levels of the tree. So it's like my move, and then their move, and my move, and their move, and my move, and their move. And then you come up with which path into that tree is the best decision for playing some sort of game. And there are a whole lot of others out there as well, data structures out there. Understanding how to do something like dynamic memory allocation and data structures and be somewhat confident at that using something like C language with pointers and nodes, but being able to understand how to allocate things like that using dynamic memory allocation, very powerful thing to understand. Now, next, and in fact, it's so powerful that you have a whole class in it next semester, data structures, and you're going to be using C and C++ to do some of that. So we've got a little bit of a head start on that right now. And I'm going to go ahead and post those example programs, along with one other additional example program, using linked lists to store not just integers, but like names, kind of like names and scores. And I'm going to post those as two handouts on the course page. But this stuff, notice, again, let me switch back to the code for just 1 second here. You'll notice that this code, there's not a lot of code here. These functions are all very short in the linked list. They're also all very short in the dynamic array. There's not a lot of code. It's not super complicated, but you'll notice, like, to add something to that array, just a few lines of code here. To delete the entire array, just 2 lines of code. To remove some item by its value or by its index, just a few lines of code for each of those. So again, this stuff is super powerful, not overly complicated to deal with. And the way that I wrote these, it allows you to see how you could add additional data items to each of these, whether it be in this structure here in the dynamic array example, or whether it's in any of these inside of this example. So it doesn't matter which one it is. It's very easy to add additional things into this structure or additional things into that structure. And notice they're very similar. The only difference is in this one, we have to have the storage for that next pointer to make a linked list out of it. All right, so I would suggest you play with those. Look at that. Again, the biggest confusion people seem to have on this one is why is it a double pointer? And that's so the function can change what's being stored in this place in memory. We give it the address of where that pointer is. It can now change that pointer to a different address. Mostly I prefer using dynamic arrays over linked lists because they're faster to index. And they're a little easier to understand because it's contiguous, and then you're also don't have memory being consumed with these pointers. But binary trees are really useful, so you might want to look at those at some point as well. But I'll post those examples, and that's it for today. And keep in mind that even though you've already taken the paper part of the final, that you still have a programming part of the final, so you might want to get familiar with some of these things because they might show up as the easiest way to do some of those things. All right, that's all for now. Everybody stay safe, wear a mask, happy Thanksgiving, and I will see you guys next week. We've got a couple final lectures to give you an introduction to C++. Clearly, C++ is its own entire language, so we're not going to have time to do an exhaustive treatment of that. So I'm going to treat it like a introductory C++. And what C++ does is it basically adds classes onto C language. It also has some other different language features that we'll touch on, but it's an object-oriented extension to C language. C language is a subset of C++. So all the stuff you've learned still works. It just gives us some extra stuff we can do by making classes, making instances of those classes. You can make arrays of instances, The classes can have methods, they can have attributes, public attributes, private attributes, so forth. But we'll talk about that next week. We have those 2 lectures of that, and you should really watch those, get familiar with those concepts, because you're going to be using that stuff next semester. All right, that's it. Thanks for the few of you who have watched this. It will pay off in the long run, I promise.